the top of the state of charge where it's not so efficient. But in a partial state of charge, lead acid technology is very, very efficient. Now, talking about solar and wind smoothing. I want to turn first to the direct renewable enhancement. And herein, the first case study that I'm going to introduce to you is a wind farm smoothing project. The objective of this project was to control the ramp rate from the wind farm, being 10% of what it otherwise would be, and to do that with about 10% of the rated power of the farm in energy terms. The objective of this particular project was to use energy storage, ultra-battery energy storage, to both smooth and shift energy. And so if you see this screen behind me, at the top we've got cloudy days and clear days. And you can see that looking at it first in terms of 2 days, you can see a clear solar day giving that typical solar profile. You can then see a cloudy day. And so I've broken out the cloud rather than to purely flatline. The second objective of this particular site was to also take energy throughout the day and feed it into the shoulder into this period here where it was more necessary or more valuable. And so working with P&M, we applied the ultra battery technology to both smooth and shift the output from that wind farm and very successfully achieved the project goals. Turning now to the enhancement of microgrids, and the very simple shift the diesel generator up into the efficient zone, you can of course increase your efficiency much, much more. And so the very simple consideration is to add energy storage to the mix, move up the fuel curve to where that green line is, and to make the utilisation of being combined and utilised in this particular way. So what we're doing here is very, very simple. On the side, we took the diesel generator, which was running inefficiently, and we paired it with an energy storage system. What we do now is we run the diesel generator sort of variable function to balance out so that you can use the diesel efficiently. The battery wanders up and down in a partial state of charge. Of course, with the battery present, you can also utilise that power control system and battery to do frequency regulation, bar correction, to basically make a silent, and that Hydro Tasmania have done some wonderful, wonderful IP where they've taken that island to where it runs renewable energy and storage alone. When you size all that up and you look at going from the small generator through to large microgrids, you reach the inevitable extreme of addressing variability on the grid if you attach all of your renewables to the grid. And so this particular site that you see on the screen now, this is a 3 megawatt regulation services facility in Pennsylvania is doing, and in this case they're turning out the full capacity of the batteries about 7 times a day. Now the batteries respond perfectly to the signal, and of course this has become quite a famous project or system in the US now, the PJM. The cost of the batteries, there's the cost of the power control system, there's also the cost of the transformer and the grid connection. And so if you want to make the economics particularly compelling, what you do is start to combine function. On the screen here is on the left is a large UPS. The picture on the right is actually of a 3 megawatt regulation services facility. If they look very similar, they are, because the battery formats are basically the same format across those two sites. System on the left sits waiting for something to go wrong. The system on the right is continuously charging and discharging. And that's the new capability that Ultra Battery introduced. So what we're doing is combining the DNA of those two products. A conventional lead, if we're using the battery in partial state of charge and we have a reserve event, we still have a very similar amount of energy available. Such that it's a much, much more profitable approach, or another way of saying that is you get payback on your investment much, much quicker. So thank you for listening to me. We've got a comprehensive product suite available of Ultra Battery from the very small.
Thank you. I will try, I know we've said this before, but I'm going to try this now. At the end for questions. David Myers from SNC Electric, is that next?
Thanks, Steve. So I'm going to talk about many of the same things that John talked about here, and some really a focus on renewables integration for this presentation. For those of you who are energy and using lots of the applications that we're talking about here, we're involved in many projects. We're in a leading position for energy storage, definitely within the U.S. And we have over 25 grid-connected products that we've been involved with. Saving other items. So on their own, each one of these applications, in many cases, doesn't make the cut. But when you start looking at the multiple values, we all know when you interconnect renewables, primarily here we'll talk about PV and wind, you need to deal with the issues of uncertainty in dispatch, the ability to be able to dispatch for the plant. And this is an area where energy storage can help, and there's real projects that are out there that can show that these technologies work to achieve these goals. So I'm going to talk about this project here. There's a lot of information available from Excel Energy. This is within the U.S. They really wanted to show that you could achieve the various things that are shown here on the slide: the peak shaving, the smoothing, dispatch, the wind, the energy arbitrage, which you can do, but in most how this works. So this one here shows the smoothing of the output. So if you look at the pink waveform, which is what was coming out from the wind turbines on their own. And the blue is the energy storage system, injecting power. So you end up with a much smoother output on this green waveform that's shown through the middle than you would have if you didn't have the energy storage. Since the energy storage can respond to those fluctuations that you see in the wind. Another thing they looked at here is being able to deal with peak demand. So this case here is showing basically a 24-hour window. Looking at a solar case, this picture is showing some of the elements of the system. The inverter and controls, the PCS, that's the area where SNC works. There's also transformers. This is a containerized battery solution. So this gives you an idea as to what one of these. So this case is paired with a 1.2 megawatt rooftop solar project. A smaller amount of renewables plant can get you the results that you're looking for. So this one's to deal with the swing. Primarily was the goal of this. So as the clouds come in, if you look at the original output, which is one labeled the original substation load, which is what the system looked like without the batteries. So you'd see swings as the clouds came over. You get more output as the clouds went away. And the load that was able to be served with this would vary a lot. Adding the batteries, which is the bottom plot that shows the battery output, you can see that it's a much smoother output for solar. So dealing with that intermittency that you get with within a community, and how energy storage can help with this. This is a project in the UK, and there's a big initiative in the UK around low carbon networks. This is a home area where they're doing many things to make them zero carbon, so that everything balances out. So these are the project drivers that the utility had in doing this and why they did it. They wanted to deal with electric vehicles that are coming. Definitely an uptake in residential solar PV in many places in the world where whether the governments and to be able to serve this. So the purpose of this, which is a demonstration project that's looking at energy storage and many other things, is to see if energy storage could be effective in helping with these actual demand that the system's seeing is the blue. The red is what it would look like on the top there without the battery, and you can see the green kind of mirroring that. And it's also keeping the peak load down at the 10 kilowatt limit for the system. So it's smoothing it out, as we've seen on the other plots, and it's also providing an ability to manage a larger peak without having to add additional infrastructure. This chart is a little bit hard to see. It actually comes from a different location, but it takes into account the community-style energy storage as to how these types of devices can improve reliability for the customers within those communities. So this particular case is showing an outage. So there's some PV here, also some PV generation. There's the battery systems and there's the utility down to a flat, down at zero. And you can see the green on the bottom, which is the battery discharging. And really what that's doing is the battery's providing the backup power until the utility system can be restored. And actually, the PV comes back up. You can see where the battery starts moving up a bit, restored. So in addition to some of the things that you can do for the solar smoothing, in these community applications, you get additional benefits that you can actually provide about a UPS function for the community to be able to deal with disturbances on the utility system so they can ride through those. And it gives the utility time to make the repairs. And particularly in a storm type of situation where many places people may be out, this offers some reliability improvements. So that brings me to my end of the presentation, and thanks for inviting me.
Excellent. The next presentation will be by Johannes White from SMA.
Existing diesel systems. We will start with having a closer look at the economy behind it, because at the end of the day, someone has to pay the bill, and it must make sense. Then we will look at the use cases of what does it is actually the use case of bringing short-term energy storage into existing PV diesel system. And then we'll take a closer look in installations that we have done just recently in Bolivia. It's a city with several thousand inhabitants. At the moment running on diesel, and we installed quite a big PV plant and short-term energy storage. So, a few words about SMA. SMA is a market leader for PV inverters. So, within a revenue about 930 million in 2013, we have plants. You see that we are at the moment in a situation that PV energy is way cheaper than energy from diesel. So the goal is the typical applications that you see here must be in a sunny region, obviously. They must run on, you reach the break-even of the investment after 4 to 5 years. And you can see with a lifetime of 10 or 20 years, depending on the site where you install the system. The main use cases, when we go into storage in such systems, it's the first thing is we want to reach a PV penetration level of between 70 and 85%, depending on the conditions on site. What you can also do is rent rate control of PV, so we have a high efficiency from it. And what we can also do is frequency control and regulation. I will show this in detail later. So, PV production on a cloudy day. So, normal day with sun, we don't have such constraints in PV production, but when you have clouds covering up and PV power goes down, we discharge the battery and thus can buffer the output that is produced by the battery. It's around 15 or 30 minute capacity when you compare the power of the inverter to the energy. Then frequency control regulation. So our inverter is bidirectional, so if we have an overfrequency due to the fact that we have produced more energy, when there is a shortage of power, we can discharge the battery. This is possible within several milliseconds and keeps the frequency in the required level. Closer look at the system in feature. You can see here the single line diagram. Key effects are known. So what we also do with the system is that we supply reactive power into the system to stabilize the voltage in all of the lines here. So here's just an overview about the 5.2 megawatt PV plant installed there. You can see it's on the Amazonas. So every lead show you what the system can do when we have installed it. What you can see here is measurements that we took on a single transit running with 400 kV. Minimum frequency is around 48.55 Hertz, and maximum frequency is 50.73 Hertz. And now we turn on some central storage in the same system. Come on. So we can see in here again 130 kV load steps. Minimum frequency is 49.87 Hertz, and maximum frequency is 50.16 Hertz. So we can really see we can react really fast and improve system.
The panelists have already addressed some of the cases that have our project that is under construction, and then I'm going to talk about a case study integrating solar and energy storage and wind energy, and then we have about 8 megawatt of energy storage projects built in Canada. And we have our parent company is a UK-based company, and then we have